Frequency protection model. Generally speaking, the over-frequency protection model is intended to offer the first and the fastest aid to electrical power system during the increase in frequency over the permitted value. As a first step for demonstration, we decided to use MATLAB Simulink model to verify our algorithm. Model is based on simplified models of power plants with initial inputs which are aligned with real power plants in electrical power system of Serbia. The model is created to make the simulation as much as close to the real system. The frequency was simulated with a calculated sequence, and the simulation in program lasts for 150 seconds for each test, and the sample time is set up to 2 seconds. Now we will open our Simulink model. In the left side of the diagram is shown a MATLAB function block which contains implemented or frequency protection algorithm. On the other side are created model of each type of power plants that you can find in energy mix of Serbia. Inside every model, for example, hydropower plant J1, parameters of transfer function are chosen in a way to give as close as possible real-time dynamics with limitation and obstacles of simplified model. Now let's start with our first test. Just to explain, the test shall demonstrate the activation of the active power decrease mechanism for hydro and thermal units. It will be simulated up to 7 seconds. The frequency is about 50 Hz, and then it rises about 50.2 Hz. Also, it is implemented variation of wind speed and consequently change production of wind turbines. The formulas for the active power decrease is briefly shown on this slide. Now let's start with test. We will run MATLAB file which contains initial inputs for the Simulink model, and as a result we will get graphics. So on the diagram you can see a change of wind speed with the two vertical red lines which represent the starting and the ending point of frequency deviation above the threshold for the active power decrease. On the next diagram shows the amount of active power needed to decrease at each point of the new calculation defined by sample time. Then we have system frequency diagram. First, you can see that the frequency is rising, and at the 7th second, active power decrease is triggered. Power plants, in this case, hydropower plants and thermal power plants, receive calculated set points to reduce production, and in the case of wind power plants, set point is equal to the current measured value and purpose to limit it in case of wind speed increase. The first 4 power plants are hydropower plants, and they are activated first. After they reach technical minimum, thermal power plants start to decrease power. The rest of the graphs represent wind power plants staying at the measured value when the active power decrease is activated. If you remember from the first diagram of wind speed between 7th and 9th second, wind speed increases. On the last diagram, you can find for each type power plants available reserve to down. You can see that for hydropower plant, the available reserve to down is completely depleted in 86 seconds. And few cycles before that, thermal power plant start to reduce production. Production for the wind power plants has been already explained before. Now we will start test number 2. This test is focused on the generator disconnection mechanism. The frequency rises above frequency threshold, that in this case is set to 50.8 Hz. It is important to mention that frequency threshold value is not hard-coded, and it is one of the inputs for starting algorithm and application later. Circuit breakers and substations which are used to deliver energy from power plants to system receive command signals for switching off. Please keep in mind that one circuit breaker within overhead tie line field can connect one or more generator units to the transmission system. The reduced sum of power in algorithm during the sending command signal for shutting down will be calculated according to knowledge of it. So to conclude, we'll send command signals in described way and not directly to generators. This only will be applied on Serbian pilot side because of technical reasons. For any other purpose where it suits, sending command signals directly to generators will be possible. Merit order list for disconnecting must be created by user and be a part of input parameters for algorithm or application as well. So the formula for shutting down frequency is briefly shown, and the active power decrease is blocked in this case. Now we will run simulation for test 2. It contains input parameters for this test, and also it will call Simulink a model, and as a result we will also get diagrams. So first set of diagrams shows status of switching device which will disconnect the generator or group of generators from electrical power grid. According to current frequency entered merit order list for disconnecting, the algorithm calculated that all generator units within wind power plants or thermal power plants will stay connected, and some hydro units will be disconnected from transmission grid. You can see the change of value from 1 to 0. The wind speed characteristics are basically the same as in the previous tests. So the next diagram will show the frequency, system frequency, that caused the activation of generator disconnection mechanism. And it returns to allowed range, which is consequence of disconnected generator from the power grid. Last set of diagrams are intended to show behavior of production of each power plant. As it's shown, the algorithm sent command signals to hydropower plant Bistrica, and rapidly after to reversible hydropower plant Bajina Bašta. So that would be all for today, and thank you for your attention.